Right, so today we're going to start episode 2, the sample size and sampling method. I'm Ayman Ibrahim, and with me now is Dr. Khalifa.
Yes, hello again.
So, starting off, we're going to start with some important definitions. And the first one would be the population. And the population basically is a complete set of people with specified characteristics. So, for example, if we make a study and we want this study to apply to Saudi diabetics, our population would be all Saudi diabetics. But in contrast, our sample would be a subset of that population that are included in the study. So if our study is studying 2,000 Saudi diabetics, this would be as our sample, but our population would be everyone, all Saudi diabetics. Another important definition is random error, and random error is basically error that occurs by chance. By chance, which occurs randomly. Things that do increase the chance of random error are sample variability, subject to subject differences, and measurement errors. And we can reduce random error by increasing the sample size or repeating the experiment so that this random error is cancelled out. But systematic error or bias is deviations that are not due to chance alone. So this could come from methods and the assessments. That, for example, if we have a scale that consistently adds 2 kilograms for all measurements, we are deviating from the true value, but we are deviating not due to chance, but consistently due to a bias. And that is a kind of systematic error. And we can reduce this error by good study design and proper procedures during the experiment. Precision or reliability is relative lack of random error, while accuracy or validity is how much a measurement represents the true value. And we can compare this more clearly visually. So if you look at these 4 examples here, if we repeat the measurement and they consistently stick together, so they don't go far away from each other, like we see on the left circle here, or on the second one from the left, where the measurements are clustering together, they're not scattering. This means that our measurement is precise, and there's less risk of random error. In contrast, if we try to arrive at the truth and assuming that the center of the circle is the truth, the more we deviate from the center, like we go up, we go sideways, that means that our measurement is less accurate. So here the accuracy again measures the true value. So the further we go from the true value, the less accurate our measurement is. So when we make a study, we're interested in what's going on in the population. That is our primary goal. So why are we picking a sample? Why don't we just study everyone? And that's a good question. Because studying the whole population is beneficial in a few ways. For example, it gives us a point estimate with no range for error because we have measured everyone. So there is no chance for inaccuracy. There is no worrying about external validity because the study is immediately externally valid if it tests everyone. There is no subgroup unaccounted for because everyone is in the study. But there are also limitations, and these limitations are sufficient to make us go for a sample rather than the population. These limitations are that studying the entire population is extremely costly. It's extremely inefficient because if you design your study properly, you will arrive at the right answer. You will arrive with reasonable certainty without having to study everyone, with having to study even a significantly less amount of the population. And again, it's just simply impossible because even if you attempt to study everyone, some of them are going to escape your study. So we're basically stuck with a sample. As long as the population is large, we are stuck with a sample. And the characteristics of a good sample are as follows. The sample should be large enough to control for random error. It should be representative enough to allow generalizability. And it should be acceptable in cost of time and money. And in order to do that, we have to think how are we going to select our sample. And with that, Dr. Khalifa is going to let us know.
Thank you, Dr. Ayman. So, how do you select a sample? So there are multiple sampling strategies that we could use when you are conducting a study. So these are divided into probability and non-probability sampling methods, or better known as random or non-random methods. So we'll focus on the random methods because they are the superior methodology depends on random sampling methods. So in simple randomization, let's take an example to understand this one. So this is the first of the random methods. So you want to conduct an experimental trial, right? A clinical trial on a small populations. Let's say, for example, students in SRU college. So you want to include everyone in the list, which is basically a list of the students in this college or in this institution or a company. And then you use a random number generator. So this is usually an application, a computer application. And what it does, it will select people randomly from the sampling list. This does not mean it will select one person and then not select the other person. This is not random. This is basically a 50-50 chance. Okay? So the advantage of this simple randomization is that the results will be generalizable. So that's the reliability part of the methodological section that Dr. Ayman mentioned. There will be is random sampling, and the sampling frame includes the whole population. So this is the list that we use to identify the participants from. The disadvantages to this, it would be less precise than the other methods that we're going to discuss next. So it's less representative than the systematic method and less precise than the stratified method. So let's go on to the systematic method first. So the systematic randomization is basically you're selecting, let's say, the third person who enters through the door to enter your sample. Okay, you have 50 people at an institution. You go up in the morning at 8 and you say, all right, every third person will be included in my sample. That's called systematic randomization. Okay, you can do this, for example, in an outpatient clinic, right? So the advantage, it's very feasible, it's very doable than other randomization methods. You do not require a sampling frame because you don't know who will be passing through that door. The disadvantage would be the generalizability would be decreased, okay? Because you do not know the sampling baseline characteristics of your sample. They might repeat, always due to random error, okay, rather than systematic error. Next is the stratified randomization, and basically this means that you need to divide your sample into subgroups. So let's take an example here. You have a big population, let's call it the city of Medina, for example, or Riyadh, and you want to represent all the groups in this city. Okay, so you want to check that the sample will include people of different ages, different groups, different ethnic origins, and both genders equally. And you do that by dividing the population into subgroups and making sure each percentage, let's say in the population, there's 60% females and 40% males. So your sample needs to be subgrouped in the same manner. So there will be 40% males in your sample and 60% females. Let's say that the adults are 30% of the population. That means in your sample, the adults need to be 30% as well, and so on in the other categories as well. This will have the main advantage of being inclusive. Okay. So in the United States, for example, they have 10% black population and let's say around 85% European origin population or Caucasian population, and maybe 5% other origins. So when you're trying to conduct a stratified randomization on the US population, your sample needs to be representative of these subgroups if you're doing it based on ethnic origins, right? So the disadvantage is that if you have multiple variables, like a lot of variables, this stratified randomization would not work, okay? You'll have to account for many subgroups, and that wouldn't be as feasible as it could be. All right, so in the cluster randomization, you're having a huge sample, let's call it multiple hospitals in a certain region, and you cannot identify all of these hospitals. You cannot go into each of these hospitals and check on the patients, for example. You need something that would be representative of these, let's say 20 or 30 hospitals. So you take a computer program and you randomly select 5 of these hospitals, 5 of the 20 hospitals in Qasim region, for example. Okay? And these will be your clusters. So you'll take the sample specifically from these hospitals that you have chosen, the 5 hospitals that you have chosen. This has the advantage of being feasible, first of all, with most budgets. This works well with student-led projects, especially projects where you have to go and take approval from institutions. So now with the cluster sampling, you will know which institution you should go to, and you'll go direct to that institution, take the sample from that place, and it will have the advantage that you do not need the sampling frame we mentioned earlier in the simple randomization. The disadvantage, again, that the results may not be, first of all, reliable. Okay, so it will have less precision than other forms of randomization, or it might have less generalizability than other forms of randomization. So now let's go to the non-random methods. Again, you should remember that the more superior quality is the random methods.
Definitely.
Yes. So we have 4. So there's convenience sampling, the snowball sampling, and quota sampling, and purposive sampling. So in convenience sampling, this is the easiest one and most common one used. You basically just put a questionnaire out there, and whoever comes and joins, that's considered convenience sampling. So it's based on convenience. This type of methodology is commonly used, but the results, again, would not be generalizable. There are a lot of bias that could occur in this, especially selection bias. Okay, there's snowball sampling. This is best used with rare diseases. Let's say, for example, people who have, let's say, HIV in a country. Okay, so you find the first patient who has the HIV infection, and then you ask them to identify other people who might have the HIV. And so you go and interview these. So you're helping these people by finding them out through the snowballing technique. So it increases in size. Every 2 will show you another 4. These 4 will show you another 8, and so on. The third technique is the quota sampling. So in the quota sampling, you need to subgroup the population, and then you fill the quota. So you have a quota of 50 patients. You need 50 patients, for example. So you find people who have the certain disease. In Ayman's example, you mentioned the diabetic patients.
Yeah.
So let's say I want 50 diabetic patients. So I'll just go to the population and pick 50 diabetic patients specifically. And once I get these patients, that's it. I'm not including any more in my study.
And to select these 50, I'm not doing any kind of randomization, no list, no clustering, nothing like that.
You just determine the subgroup, which is diabetic patients, and you just add them into your study. So this is quota sampling.
Right.
Purposive sampling, which is the final non-random method, basically means that the researcher decides, okay, this participants would do well in my study. For example, in a study on statins, I could say, you know what, I'm gonna choose overweight and obese patients to test my drug on, for example, in a clinical trial, and then I do purposive sampling. This is a non-random clinical trial.
Or maybe I think that, for example, John or Mohammed is gonna stick to the medication, so I choose them because I think they would do a good job in the study, right?
Yes, so that's another aspect of it. So it is full of potential holes for systematic error to occur.
Definitely.
Okay.
Yeah.
So whatever you do, try to use the random methods first, and if you couldn't do those, then try to do the non-random methods in the most correct way possible. All right. So next we'll be doing the sample size.
Yes. Then after perhaps we know how are we going to select our sample, we have to decide how large does it need to be. So to ask the question, we need to know that. I mean, it's a difficult question. How large our sample needs to be. There are a few things that we need to fulfill. For one thing, we need to a large sample that is large enough to minimize random error, because if we have a small sample, there's a more chance of inaccuracies, more chance of random error. We need it to be small enough to be feasible in time and money. So we need to balance these two, basically.
Especially with limited budgets that are given in students' projects, for example.
Especially, yeah, exactly, that's true.
Okay.
And how do we choose the right sample size? We need to, one way is using experience, but for that you need to be an expert in the field. Another aspect is measures of significance. That depends on the alpha. Powers of the study, that depends on the beta, and the expected effect size. And we're gonna explain how the last three kind of relate to the size of the sample. So what we try to achieve is the truth, and what we find in the study could be consistent or may not be consistent with the truth. So if you look at this table, where we would like to be is here or here, where there is an area where we are consistent basically with the truth. If we don't find an effect in the study, we would rather that that lack of effect is real, and if we do find an effect, we would rather have that effect as a real effect. And we do our best to avoid being in these two scenarios where we find an effect that does not exist, or we miss an effect that really does exist.
So we're basically avoiding a type 1 error and a type 2 error.
That's exactly
Okay.
right.
All right.
And the probability of doing a type 1 error is basically the alpha, right? That is basically the chance that we accept in our study. We say that it is possible with our design that 0.05% or 5% of the time that we will find an effect that doesn't exist, and the beta would be what we decide as an acceptable margin for missing an effect that actually exists. And it's upon these two values, our sample size is gonna change. So if we have a stricter alpha and we have a stricter beta, so we don't want to miss any effect that is real, or to find an effect that isn't real, we have to have a bigger sample size. The third effect that perhaps that influences the size of the sample is the effect size. And the larger effect size there is in reality, the easier it is to find it. And that's why it would require a smaller sample size. And perhaps a small example would help this become more clear. Assume, for example, or imagine that there is a large bathtub, and that bathtub is full of water. If you put 1 spoon of salt, a small effect size, it's going to be very hard to discover that amount of salt, right?
True.
But if you find, for example, if you put 10 kg of salt in that, and you take a small spoon, you can immediately taste that salt. So even with a small sample, you can taste a large effect size.
True.
But if the effect size is small, then you gotta have a lot of data. You gotta collect a lot of participants in order to find that very small size. And the effect size, basically, one of the ways to measure the effect size, especially if in a quantitative scenario, is the difference between the means divided by the pool estimated standard deviation. And perhaps it makes sense that the estimated difference in means would affect the effect size, because that means that there is a significant difference, or a big difference that is easily visible. But how does the standard deviations affect this? And perhaps it would help us to look at this visually. So assume that, for example, you are testing 2 drugs, and you are finding their effect on, blood glucose. Assume this is below here, this is blood glucose. So when you give drug A, the mean is somewhere here, of blood glucose somewhere here. If you do take drug B, the mean is somewhere here.
Mm-hmm.
And there is an overlap between them. And this overlap is basically the area where there is no difference, right? This is the chance that there is really no difference between these 2 drugs.
Mm-hmm.
So if there is a large difference between the means. Like, look here. For example, this is the mean for drug B, this is the mean for drug A. There is a big difference. There is little chance that there is no difference between them.
Right.
And that means that the effect size is large. At the same time, if there is smaller standard deviations, as you see here, so they're kind of narrower. And this will also kind of constrict the area of overlap between them. And that also makes ensures that the similarity does not exist, or that there is a difference between these two groups, or that the difference is real. So if you have a larger difference between the means, if you have a smaller standard deviation, all of these increase the effect size, and therefore you will need a smaller sample to find the real effect. So calculating the exact sample size depend on these three factors, that is the accuracy. But other factors that will also influence the sample size would be the study design and what kind of outcome, or the main outcome measure of the study, whether it's categorical, whether it's continuous, and how many groups. So there are distinct approaches for calculating sample size for different study designs and different outcome measures. In order to do that, there are a lot of computer software that helps us to calculate the sample size, as long as we understand the theory behind it. These examples include EpiInfo, Inquiry, Power and Precision, Stata, SPSS, and what is commonly used is online calculators because they're easily accessible, as long as they have the documentation behind their methodology. And perhaps now Khalifa is going to show us an example.
All right, thank you, Ayman. All right, so here's an example of an online calculator. So this is from clinicalcalc.com. So in this website, you can find that it allows you to multiple options depending on what kind of study design you're doing. So let's say you're doing 2 independent study groups, which is the usual case. And then you're trying to find the primary endpoint. So that primary endpoint is either, let's call it binary, so dichotomous outcome, categorical outcome, or continuous. So that's based on means. And this is important in this next stage. So you can see here on the left, it says anticipated incidence. And that's because we chose the dichotomous one, the dichotomous variable outcome. So what you see here is that it tells you what's the anticipated incidence in group 1 and in group 2. And then it calculates the expected effect size from these two variables. The enrollment ratio is basically the how many people are going to enter the control and the intervention group. So 1-1, that's how it works. On the right side, you find the type 1 and type 2 error rate. So the alpha is set at 0.05. That's its usual setting. Some studies would put it at 0.01. It's a more stricter criteria. The power is a bit lenient, so we usually put it at 10 to 20% allowance for error rate. So you can see here the power is around 80%. So that's a 20% allowance for error rate.
Because the power, of course, is 1 minus beta. If we decide the beta is 0.2, then the power would be 80%.
80%, yes. So if we chose, for example, in the primary endpoint, we chose its continuous variable, so it's means. So in the anticipated part on the left side, you'll find that it will compare the two means of the two groups.
Yes.
Okay, that's the difference. All right, pretty easy and straightforward, I think. So take home message. So basically, the sample size calculation and the accuracy of your sample size estimation are dependent on certain factors. So let's go with the sample size calculation first. So it depends on the study design. So you'll need to check online after you choose your study design, which form of calculation works best. Okay, we've put some references for you. You can find them down below in the description or in the Notion page. Okay, so you need to read these articles and you'll find a lot of knowledge there that could benefit you. Okay, the other thing is the main outcome measure of the study that we just described right now. For the accuracy of your sample size, this would mean that you need to know the estimates of the effect sizes, the power, and the random error. All right.
Yeah.
All right. So we have some references over here. These wonderful people that helped us out, and I'm sure that they can help you out too if you read their material as well.
Yes.
You can use these useful links. You'll find them, like we said, below or in the Notion page. Thank you very much, Dr. Ayman.
Thank you. It was a pleasure.